Everything has a natural frequency at which it wants to vibrate. If you have two kids on a swing and you give one of them a push, then that kid will swing back and forth with a very predictable frequency, corresponding to the natural frequency of the swing. If I hit the whiteboard with my fist, you hear a sound. The sound that you hear corresponds to the natural frequency at which the whiteboard wants to vibrate. If I blow across the top of a water bottle, you hear a sound that corresponds to the natural frequency of the water bottle. Everything has a natural frequency at which it wants to vibrate. That natural frequency is called a resonant frequency, the natural frequency at which something will vibrate. Everything has one. The natural frequency of the whiteboard is different than the natural frequency of the water bottle, which is different still than the natural frequency of the swing set, but everything has its own unique natural or resonant frequency. Now another term that's related but not quite the same thing, resonance. If I apply a force that matches the natural or resonant frequency of whatever it is that's vibrating, then I can cause the amplitude of vibration to grow. For instance, if I've got a swing set with a very particular natural or resonant frequency, and I push the person on the swing set at just the right time, if I push that person at a rate that matches the natural frequency of the swing set, if I push that person every time they come back to the same spot, then the amplitude of vibration of that swing set will grow. That's called resonance, a phenomenon where the amplitude of vibration increases when a force is applied on an object at the rate that matches the resonant frequency of the object. You know, when you're on a swing set, if a person pushes at just a random rate, you're not going to swing higher and higher and higher, but if they push at just the right rate, at the resonant frequency, the natural frequency of that swing set, you will start swinging higher and higher and higher. In other words, resonance has just occurred. You've just matched the resonant frequency, you've just caused the amplitude of vibration to grow.
Let's look at a vibrating string. On the left-hand side of the screen, you see a mechanical wave generator that's producing a wave. I'm increasing the frequency of this wave. As I send that wave down, it reflects off of the pole on the right-hand side, comes back, interferes with the wave that's still being produced. If I match the natural frequency of the string, you see what you see on the screen right now, which is what a wave that appears to be standing still. We call that a standing wave. If I slow that down a little bit, you can see that the string is still moving back and forth, up and down. It just appears to be standing still. Increase the frequency even more, I see another standing wave produced. A second harmonic, we call it a second resonant frequency. If I slow that one down, you can see that that string is still moving back and forth once again. It just appeared to be standing still. Increase it even more. Let's find a third resonant frequency. We call this the third harmonic, the third standing wave. Wave appears to be standing still, just like it did in the first and second harmonic, but if I slow it down again, you're going to see that the string is just moving back and forth, back and forth, back and forth, like it was before. The resonant frequencies, or the standing waves produced by this string.
Now I want to apply this whole concept of resonance and standing waves to a little bit of music theory. This is a guitar. A guitar has 6 strings, and each of these strings has a natural frequency or resonant frequency at which they want to vibrate. If I pluck one of these strings of the guitar, let's say the top string, it will vibrate at a whole bunch of different frequencies initially, but most of those frequencies will die out. The only one or ones that will remain, the only frequency or frequencies that will remain for any length of time at all are the ones that correspond to the natural or resonant frequencies of that string. Let's see if we can figure out what that frequency is and how it would be produced. The demo that you just saw showed several different standing waves produced. If you remember, the one that looked like this was called the first harmonic. If I pluck that top guitar string, it will always produce that first harmonic. Let's say, in this case, that first harmonic corresponds to a frequency of 83 hertz. Now that depends upon a number of factors, but just for argument's sake, in this case, let's say it corresponds to 83 hertz. The second harmonic would look like this, and the second harmonic frequency would correspond to 166 hertz, twice that first harmonic. The third harmonic would look like this, and the third harmonic frequency would be 3 times the first harmonic frequency, therefore it would have a value of 249 hertz. When you pluck that top guitar string, the first harmonic is the one that you will hear. That's the pitch of the note that you will hear. The second harmonic you may hear in combination with the first harmonic, you may not. The third one you may hear in combination with the first harmonic, you may not. Other frequencies that are in between those harmonics will quickly die out for sure, and you won't hear those. Now, if you hear just the first harmonic, again, you will hear that sound of 83 hertz. But if you hear that first harmonic in combination with the second harmonic, you're still going to hear a frequency or a pitch of 83 hertz, but the timbre of the sound will be a little bit different. In other words, the richness of the sound will be a little bit different. You know that sometimes a musical note sounds one way, sometimes the same note sounds a little bit different. The timbre or the richness of the note depends upon whether you have the first harmonic, just the first harmonic, or the first harmonic in combination with the second harmonic, or the first in combination with the third harmonic, or some other combination of those harmonics. How do we know which harmonics we actually hear? We know the first harmonic when I pluck that guitar string, that top guitar string, is going to be 83 hertz. We know we're going to hear that sound. That is the pitch of the note that we hear. But how do we know if we're going to hear that in combination with the second harmonic and or the third harmonic or the fourth or fifth or whatever harmonic? Let's say that we pluck this top guitar string in the middle of the string, right here. If we do, we will for sure hear the first harmonic. You can see that in the middle of that guitar string, the first harmonic produces an antinote. So that string is going back and forth, back and forth, back and forth, up and down. We will definitely hear that sound. The third harmonic we will hear as well, because there's an antinote there. But if we pluck the guitar string in the middle of that top string, then we will not hear the second harmonic in combination with the first and third harmonic. The timbre of this musical instrument will be dependent upon the first and third harmonic, as opposed to the first, second, and third harmonic. The frequency or the pitch that we will hear is still 83 hertz, but it's a different level of richness than it would be if it was just the first harmonic. Now, if I was to pluck this guitar string a third of the way down, let's say right here, let's pretend that's a straight line, then we would still hear the first harmonic, because the first harmonic has the string going up and down, not quite an antinote, but almost like it was when we plucked the guitar string in the middle. We will also hear the second harmonic, because that string is vibrating back and forth, back and forth, back and forth at that position for the second harmonic as well. But we will not hear the third harmonic, because a third of the way down, the third harmonic has a node. And at that point, we have destructive interference, and at that point, the string isn't actually moving at all. So, if we pluck the guitar string in the middle, we will hear a pitch of 83 hertz, but that 83 hertz will be in combination with 249 hertz, so the timbre will be a little bit different. If we pluck this guitar string a third of the way down, we're still going to hear a pitch of 83 hertz. The note that you hear on that guitar string is the same, but it will sound a little bit different than when we plucked it halfway down, because this time we hear that 83 hertz in combination with the second harmonic rather than in combination with the third harmonic. So how do we predict exactly what frequencies this is going to occur at? Let's draw this out. That would be the first harmonic. The first harmonic will always correspond to V, V being the speed of the wave, over 2 times L, L being the length of the string. The first harmonic is whatever the speed of the wave is divided by 2 times the length of the string. The second harmonic, you remember it looks like this. The second harmonic, easy. It's just twice the first harmonic. So if the first harmonic was 83 hertz, then the second harmonic would be 166 hertz. The third harmonic would look like this. Notice we had 1 antinode, 2 antinodes, 3 antinodes. The third harmonic has 3 antinodes, and its value is 3 times the first harmonic. So again, if that first harmonic was 83 hertz, then the third harmonic would have a value of 3 times that value, or 249 hertz. Let's do a problem. Example number 1 says the speed of sound in a particular guitar string is 420 meters per second. That's a little bit higher than it would be in air. Well, that's because the sound travels faster in a metal string than it does through air. The length of the guitar string is 75 centimeters. I'm going to circle that because it's non-standard units. We always want to be in meters here. What are the frequencies of the first 2 possible harmonics produced? Let's write down a couple givens here. Speed of my wave is 420 meters per second, and the length of the guitar string is, converting that to meters, 0.750 meters. Let's find F1, and let's find F2. F1 is equal to V over 2 times L. V is 420 meters per second over 2 times 0.750 meters. We calculate that, it works out to be 280 hertz. So the first harmonic, the pitch of the note that you would hear if you plucked this guitar string would be 280 hertz. The second possible harmonic doesn't mean we'd hear that necessarily, because sometimes you know that you hear the first harmonic and the second, sometimes you hear the first harmonic and the third. But the second possibility, depending upon where you pluck that string, would be 2 times the first harmonic. So we simply say 2 times 280 hertz, which gives me 560 hertz. The second possibility, the second harmonic, is 560 hertz. Let's take a look at one more example for now. This one says the frequency of the third harmonic produced in a guitar string is 76.0 centimeters. Sorry, the frequency in a 76.0 centimeter long string is 783 hertz. What's the speed of sound in the string? So I'm going to say not F1, but F3, the third harmonic, is 783 hertz. And I'm going to say the length of the string is 0.760 meters. I want to find V, the speed of sound in a wave. Now, we know that F1 is V over 2 times L. But I don't know what F1 is. So I'm going to find F1 over here by saying F3 is 3 times F1. F1 is therefore equal to F3 over 3. So in other words, it's 783 hertz divided by 3, which gives me a frequency of 261 hertz. If the third harmonic is 783 hertz, then the first harmonic is 761 hertz. Now what I'm going to do is just take my equation that I learned a few minutes ago and rearrange it. V is equal to, take the 2L up by multiplying, 2 times L times F. The length of it is 0.760 meters. The frequency is 261 hertz. Remember, if you're using this equation, you always have to use the frequency of the first harmonic in the equation. If you don't have it, then get it. 2 times 0.760 times 261 gives me a value of 397 meters per second. The speed of sound in this particular guitar string is 397 meters per second. Now, in just a moment, I'm going to move on to another kind of musical instrument, which works on the same fundamental principles. Looks a little bit different, but fundamentally the same. But before I do, I want to draw your attention to something. I go back to my picture of the guitar for a second. How is it that I can change my note on a particular string? So let's say the frequency or the pitch of that first string is 83 hertz. How can I make it 100 hertz? Or how can I make it 60 hertz? Well, there's a couple of ways that I can do that. You remember that the equation that describes the first harmonic is V over 2L. If I increase the speed of the wave, if I make the wave travel faster through that string, then the frequency of the first harmonic, in other words, the pitch that I hear, will also be higher. How do I make the speed of the wave faster in that string? I tighten it. You tighten the little tuner thingy over here, make the wave go faster, increases the frequency. And you know that if you've ever played with a guitar before. If you tighten the string, the pitch that you hear when you pluck that string is higher. Now, what's the other way? Well, the other way of changing the pitch of a string is to put your finger on a fret. If I put my finger on a fret, what I'm effectively doing is shortening the length of the string. L is smaller. If I make L smaller, since L is on the bottom, then I make F bigger. Put your finger on a fret, shorten the string, increase the frequency of the first harmonic, or in other words, increase the pitch of the sound that you hear. So 2 ways to change the pitch that you hear. 3 ways, really. Put your finger in a different place. That's not going to change the pitch that you hear, but it is going to change the richness of the sound that you hear, or the timbre. The second way, this way is to actually change the pitch that you hear, is to change the speed of the wave by adjusting the tuning knob. And the third way is to put your finger on a fret, which is effectively going to reduce the length of the string, which increases the frequency. What if you have a clarinet or some other musical instrument that's not the same at both ends? A guitar string is the same at both ends, right? It's attached at both ends. If you have a clarinet or a flute or some other instrument like that that you blow into with one end open and one end closed, then you will still get a first harmonic produced, and that will be the pitch of the sound that you hear, but that first harmonic would look different. The air, not the string this time, the air would vibrate back and forth to produce a first harmonic that looks like this. Notice, in this case, we have a node at one end and an antinode at the other end. The frequency of the first harmonic this time, notice it's V over 4L. For the guitar string, it was V over 2L when it's what we call a closed air column, like a clarinet or a flute, open at one end, closed at the other end. The frequency of the first harmonic is the speed of the wave divided by 4 times the length of the wave. The second harmonic would have 2 antinodes again. But remember, we have to have a node at the closed end and an antinode at the open end. This sound would not be twice the first harmonic, but this would actually be 3 times the first harmonic. The next one would look like this. We had 2 antinodes, now we have 3 antinodes. But this one would not be 3 times the first harmonic, this one would be 5 times the first harmonic. So, what am I telling you here? When you have a guitar, the sound that you hear, or the timbre of the sound that you hear, will be the first harmonic, and then that sound in combination with maybe the second, maybe the third, maybe the fourth harmonics. The timbre of the sound that you hear with a clarinet or some other musical instrument like that will not be the first, second, third. It will be the first, third, fifth, because those second harmonic and the fourth harmonic, and all the other even numbered harmonics just don't exist. When I blow into the mouthpiece of a clarinet, the reed vibrates, and it produces all kinds of different frequencies, even frequencies other than what you see up on the board here. They quickly die out. The only ones that can possibly remain are the first, third, fifth, etc., versus the first, second, third, etc., for something like a guitar string. Now, the way we solve these problems is pretty much like it was for the guitar string, except the equation, obviously, is just a little bit different. And we have to remember that there is no such thing as the second harmonic or the fourth harmonic or any other even-numbered harmonic. Let's take a look at one example for this. Example number 3, it says, determine the frequencies of the first two possible harmonics. Remember, the first two possible harmonics in a closed air column, like a clarinet, would be F1 and F3. There is no such thing as F2. The length of the air column is 45 centimeters, and the temperature of the air is 20 degrees Celsius. We haven't seen that since last week here. The temperature of the air being 20 degrees Celsius just allows us to find the speed of sound in air. So the length of the air column is 0.450 meters. Temperature of the air is 20 degrees Celsius. We're looking for the first harmonic frequency. That would be the pitch that we would hear when we blow into the mouthpiece of this clarinet. And we're looking for the third harmonic, the next possible sound that we would hear in combination with the first harmonic. So I'm going to say V, first, the speed of sound is 331 meters per second plus 0.6 times T. Remember that one? 331 plus 0.6 times 20 gives me a speed of sound of 343 meters per second. This equation, by the way, wouldn't work for the speed of sound in a guitar string. It only works for the speed of sound in air. Works for these closed air columns, though, because, of course, in a closed air column, a clarinet or something like that, we're looking for the speed of sound in air. All right. Now let's find the first harmonic. Remember, it's not V over 2L like it was in the last two examples. It's V over 4L. So 343 meters per second. Notice that speed of sound is a little bit smaller than it was in a guitar string, right? We would expect that. 4 times the length of 0.450. That gives me a frequency of the first harmonic of 190.5555 or 191 hertz. When you blow into a clarinet, the mouthpiece of a clarinet, the reed vibrates and produces a fundamental frequency or first harmonic of 191 hertz. That is, if the temperature is 20 degrees Celsius and the length of the air column, the length of the clarinet is 0.450 meters. You will hear that fundamental or first harmonic frequency of 191 no matter which other harmonics stick around. The only difference will be the timbre or the richness of the sound. If we hear the second possible harmonic, which is actually the third harmonic, in combination with that, then that third harmonic would have a value of 3 times 190.5556, which gives me a value of 572 hertz. So for sure, we'd hear this one in the clarinet. We may also hear, in combination with this one. The pitch that would come out of the clarinet would still be 191, but the richness of the sound would be different if we heard it in combination with the 572.